right, so we're looking at writing and interpreting linear functions 2 notes. And what we want to do on this is we're just going to work on answering questions, pulling strategies together. Okay, so the notes are just some examples of what could show up on your worksheet and then later on your test. So what expression can be used to find the values of S of n in the table below? Okay, so you notice S of n is here on the table and we're missing these two. Okay, and we know from our function notation this is similar to our y values, right? Okay, and they've given us expressions, so what we're going to do is they're saying all of our expressions have an n. We're doing something to n and we're creating our S of n. Okay, so one of the easy ways to do this is to figure out what works of these equations for the different numbers. Now, what I like to do is, because when it's multiple choice, usually the people who create multiple choice questions, they make them work for the first and maybe the last, but usually the equations don't work for the middle numbers. So I always pick a set of numbers from the middle of the table, and I would just say, in this case, that would be 3 from right here, and then I would replace n with 3, and I would get 9, which is not 11, so it can't be A. And then I would similarly try the other. So 5, replace n with 3, and I get 15, which again is not 11. Okay, and then here n with 3, so 3 plus 4, which is 7, which is, well, you guessed it, not 11. Okay, so the answer must be D, so let's try it out. 3 times 3, placing n with 3, plus 2, 9 plus 2 more is 11, so we have a winner. Okay, let's take a look at another question. Which algebraic expression best represents the relationship between a term in the sequence below and its position in the sequence? Okay, so this is in position 1, this is in position 2, this is in position 3. You're getting the hang of this? Okay, so 4 and 5. Okay, and so it's which algebraic expression best represents the relationship between a term in the sequence and its position? Okay, so here what we're saying is our n, right, is going to be the position it's in the sequence, and then how do we get that number, right? Okay, so if I put 1, well, I'm not going to try 1 because, like I said before, if we start at the beginning, those numbers usually work, and sometimes the ones at the end work. So I'm going to go with my theory here and just stick with the middle. Okay, so this would be 3 minus 1, which is 2, but it's not 8, which is what we need it to be. Okay, n squared, so that would be 3 squared minus 1, okay, which is 9 minus 1, which is 8. Okay, it matches, but I have to check the other answer choices to make sure none of them match. Okay, so here we're going to have 3 times 3 minus 1, which also gives me 8. Okay, and then 2 times 3 squared minus 2. Well, let's see, 3 squared is 9. 9 times 2 is 18. 18 minus 2 is 16. That one's not equal to 8. So we've eliminated the n choices. Now we got to check these middle choices here. Okay, so the easy thing we got to do is we pick the next set, and here we'll say 4 squared minus 1, and here we'll say 3 times 4 minus 1. Okay, just following the pattern. This 4 squared is 16, minus 1 is 15. So we have a match right here. Okay. And then 3 times 4 is 12, minus 1 is 13, and that one didn't work. So it worked for the first time we checked, but this one didn't work the second time. And the deal is these equations have to work for every time. Okay, so G would be our choice there. Which sequence uses the algebraic expression 4n plus 5 to describe the relationship between a term in the sequence and its position in the sequence? Okay, so this is a similar question, only now they've given us the expression and asked us for the sequence. Okay, so 4n plus 5, for this one I'm going to work just with the idea of creating the sequence from this. Okay, so if we look at this, this is position 1, 2, 3, 4, 5, then we could create a table, right, for n is 1, 2, 3, 4, and 5, and then we would just figure out what the term would be. Okay, so this will give us our term. So if we're in the first position, our term would be 4 times 1 plus 5, which is 9. So that eliminates choices A and B. So then we go to the next one. 4 times 2 plus 5 would be 8 plus 5, which is 13, which eliminates choice D. Okay. Now, just to be on the safe side, we'll go ahead and check the others. So this would be 4 times 3 plus 5, which is 17, and that's a match. 4 times 4 is 16, plus 5 more makes 21. And then 4 times 5 plus 5, okay, that would be 4 times 5 is 20, plus 5 is 25. So we have a perfect match there. Okay. Let's check out another one. Mrs. Whitaker used identical square tiles to design the 4 figures shown below. Which expression can be used to determine the number of square tiles used in each figure if n represents the number assigned to the figure? Okay, so this is n is 1, n is 2, n is 3, n is 4, and we have 1, 2, 3 tiles, 4 tiles, 1, 2, 3, 4, 5 tiles, and 1, 2, 3, 4, 5, 6 tiles. Okay. So, just going to pick one here from the middle. I'll try 3. So this would be 3 times 3, which is 9, which is not equal to 5. Which is what we're looking for. Okay, so 3 squared plus 2 would be 9 plus 2 is 11. Again, not 5. So we're not going to be able to select F or G. Then 2 times 3 plus 1. Well, let's see, 2 times 3 is 6, plus 1 is 7, which is not 5. And then J is 3 plus 2, which is 5. Okay. So J is going to work, and we can double check. 1 plus 2 is 3, 2 plus 2 is 4, 4 plus 2 is 6. So we are definitely taking the number and adding 2. Awesome. Mr. Lyons invested some money that will double in value every 12 years. If he invested $5,000 on the day of his son's birth, how much will the investment be worth on his son's 60th birthday? Ooh, that sounds tricky. Let's see. It doubles in value every 12 years. So I'm just, I like a table. I'm going to try a table for this one because this is years old, right? And then this is money. That's what we've got related here. So at 0 years, right, because the day of his son's birth, so that's 0 years, there was $5,000. Okay? And so if it's in there 12 years, it's going to have doubled, so that would be $10,000. And then the next 12 years would be 24 years for his son, and that would be $20,000 if it doubled. Okay. And then the next 12 years would be 36, and so that would be $40,000. Let's see. So we keep going till he's, what, 60? But let's see. So 12 more years would be 48. 12 years after that would be 60. Oh, that's not too far. We can do that. So 40,000 doubles, that's going to be $80,000. And if 80,000 doubles, that's going to be $160,000. Okay, so that would be answer choice B. Okay. The table below shows the number of sides and diagonals in certain polygons. Number of sides, number of diagonals. Got it. Okay. Based on the table, how many diagonals should a 9-sided, convex polygon have? So that means if we extended our table on out till 9, then what should we expect to see happen over here? Okay. Well, let's see. Here we went up 1, and here we went up 1, and here we went up 1. So it looks like my pattern's increasing by 1, the number of sides. So let's see what's happening here. We increased by 2, and here we increased by 3, and here we increased by 4. So this is not a linear pattern, because a linear pattern would have the same number here each time. So right now, the only way we could solve this is just by continuing the table, because all we know about right now is linear patterns. So if I increased 1 more, right, that would be 7. I'm going to bring that over here. We're just going to start with this bottom line. We have 6 and 9. So if we increase 1 more, that's going to be 7. And since the last time we increased was 4, and our pattern seems to be 2, 3, 4, I would expect to increase by 5 here. So 9 plus 5 is 14. And then we increase 1 more, and we're at 8. So we'd increase by 6, which gives us 20. And then if we increase 1 more, we're at 9. And here we would increase by 7, so that would be 27. So a 9-sided convex would have 27 sides. Okay, that was a little bit tougher. The thing you're going to have to be going through for your worksheet is you're going to just be analyzing each one and seeing what's going on, and then making predictions. A lot of these have tables. So if you'll recall, if you want to use your calculator for tables, you choose the spreadsheet option, okay, and then remember to put information here at the top, right? You have to like put X and Y or N and Z or whatever letters you want you're using for that particular problem, and then you put your numbers in for each column, okay, and then you can use your menu, which allows you to take certain actions or analyze things as you need to. Okay. All right. One of the big ones was stack calculations, and then we did linear regressions. But we saw in that last one, a linear regression wouldn't have helped us because it wasn't a linear pattern. So you might have tried one of these other types of regressions, which we haven't studied yet. So you may want to just stick with, if it's a linear, you can use your linear regression to get your equation. But other than that, I don't think I'd be messing too much with the regressions. All right. Go forth and conquer.